finish the one you're on right now, let's talk about at least the first couple. Alright, so before we actually attempt to analyze the graphs, tell me a couple things you can automatically tell from photoelectron spectroscopy graphs. Christian's table, give me one thing you can tell. Say again? Number of electrons in the whole entire atom, right? From inside to out, okay? So you're looking at peaks for that, right? Emily's table?
Electron configuration.
Okay, so not only how many electrons, but the actual electron configuration. Drew's table?
Intensity.
What does that mean?
Like, based on the number of electrons.
So we said number of electrons total like an atom. We said electron configuration. So you're saying how many electrons are in a given subshell?
Yeah.
Okay, so the intensity is very specific in a given subshell or particular sublevel. Taz's table? Say again? So binding energy meaning the energy that the electron is bound to the nucleus by, right? So what kind of electrons are highly bound to the nucleus?
Inner core.
Right, so the inner subshells, right? So at like 1s and 2s and 3s and 2p, it kind of depends, right? All right, so we should be able to tell a lot of information. Remember, the graph is backwards, right? So the way I try to explain it is that we pretend the nucleus is over here. So if we pretend the nucleus is over here, we can think about how the maximum energy is going to be closer to the nucleus because it's highly attracted due to what attraction? Say it again? Coulombic attraction, right? And then as we go away, the distance gets farther away from the nucleus. These electrons are less highly bound or have a lower binding energy, lower megajoules per mole, electron volts. There's a lot of units I can use for this. All right, and then this is relevant because we're talking about atomic structure, and you should be able to relate. And this is like on the very last, one of the last pages. I have an alarm going off to remind me to tell you guys we got to make sure we sign up for AP exams. Raise your hand if you've already signed up. So after my cry for help last week, a lot of you did. Mrs. Landon hasn't updated it for me, so I can't see everybody's yet. But we'll make sure we do that today. Okay. Anyway, so this is relevant because now we have interchange between a lot of different diagrams and displays that would give us information about atomic structure. This is called a what? Bohr diagram, which we never actually draw, but this correlates with the PES quite a bit. This is just a blob of an atom. This is a off-ball diagram, right? Also known as an orbital diagram. Just it's layered in energy levels, so it's technically called an off-ball diagram. And then this electron configuration. So all of these correlate, so we should be able to interchange between those quite easily. All right, so this one has answer choices for you guys, right? Do you have answer choices on yours? All right, so regardless, okay, so what does this peak represent? 1s2. It has to be 1s2, right? It can't be 1s1. Why? Because there's more. Okay, so first of all, there's more. You have to fill up the first energy or the first subshell. All right, so that's 1s2. This is 2s2, and this represents. How do you know it's 2p3 and not 4? Right, so the intensity is 1/3 more than what this is. So apparently, for every 2 little grid lines, it's a 1 electron. So that's 2 for those, and then plus that last one would be 3. So who is this? Nitrogen. Why is the 2p energy or 2p peak farther to the right? Okay, so less attraction. Okay, but these are both in the second energy level, right? So theoretically, same distance from the nucleus. What is the S undergoing? Nuclear penetration. Good. Okay. Which is fine. This explains the relative resistance intensity of 2s for the following: lithium and beryllium. So you have A, B, C, and D. Here's your letter scheme: A, okay, B, C, and D. All right, go for it. So let's sign language today. Okay, so most people are saying A, and that is correct. Okay, so in terms of what we're looking at is positioning. The berylliums, this is what shell? 2s, right? So 2s is way over here at 11 for beryllium, but over here at 5 for lithium. So it's showing you that lithium has weaker attraction to its 2s shell, and the only reason that should be, because we're talking about the same shell at 2s and 2s, is what? Number of what? No, number of electrons doesn't matter because we have the peak. Oh, sorry, is this the intensity question? Sorry, I might be looking at the. What's the next one? No, the sodium one's next. No, this is it's talking about the positioning of the peak, not the size of the peak. Because remember, size of peak represents what? Number of electrons, right? Positioning of the peak represents so energy of attraction, which really relates to what? Coulombic attraction, which really relates to what? Z. Okay, nuclear effective charge. So in this case, lithium has 3 protons and beryllium has 4 protons, right? So in both of these cases, you're just looking at the 2s sublevel. They're both equally distanced from the nucleus, theoretically, but lithium is lesser attraction than beryllium, so beryllium is more attraction, means that the greater nuclear charge will cause more binding energy to be relevant here. And then the more electrons in the 2s orbital just tells us the peak is bigger versus the lithium one. So it should be A. All right, most of us got there, okay? Given photoelectron spectra for phosphorus and sulfur, which of the following best explains why this is a loaded question, why the 2p peak for S is further to the left than the 2p peak for P, but the 3p peak for S is further to the right than the 3p peak for P. Woo. All right, so you have answer choices. These are teeny tiny. Here we go. All right, answer in 3, 2, please. Show me your hand, people. I would say 70% of us are saying A. A couple of us are saying D and C. All right, so let's think about this. S and P, right? First of all, we have to consider 2 things. Distance from the nucleus and attraction to nucleus. Sulfur has how many protons? How many? 16. And phosphorus has 15. And if we're looking at the 2p, which of these is 2p? So this is what? Let's just label it. 1s2. This other next one is what? 2s2. This is okay, 2p6. And then this is 1s2, 2s2, and 2p6. So what's the big difference between this one and this one? Right, so binding energy, meaning position on this graph, which the graph's kind of crappy. It's hard to tell that graduation. So they give you the they give you the binding energy here. So 13.5 versus 16.5. So who's more tightly bound? Who? Sulfur's 2p. Okay, so that's why it's saying it's to the left. So first off, why should sulfur's 2p be more tightly bound? More protons, higher Zeph, right? Okay, so A, sulfur has a greater effective nuclear charge than P. So far, so good, okay? And B also says that, okay? Sulfur has a greater number of electrons than P. Would a number of electrons affect how tightly it's bound? Not for this particular one, because they both have what in their, well, no, this one's not 6. No, that is 6, yeah. So both of these have 2p6, right? So they're not going to differ in terms of their like electron pulsion or anything in that level. Okay, so then the next question was for the 3p. So this 3p peaks over, this is 3s2, this is what? 3p what? 3p3, and this is 3s2, and this is 3p4. Okay, so this one's a 1.06, and this is a 1.00. So who's more tightly bound to the nucleus? Phosphorus. Why? Versus sulfur. Say again? So it's not just the fact that it's more electrons, it's that it has electrons where now? So like think about how this is 3p3, so it goes 1, 2, 3, 1, 1, 1. There's an equal number of electrons in each. There's no additional electron repulsion because they're all in separate orbitals. This one has a doubled up area. So it's not only the fact that there's more, because like you could have had 1 and 3 and it wouldn't have made much of a difference, but it's because you've gone back and now had to double up, creating additional electron repulsion. So the 3p sublevel S has a greater electron repulsion than P. Answer is A. So if you write out your electron configuration across the board and you think about what's happening in that last one, you should hopefully see the 3 go to 4 and then say, oh, I'm now doubling up, that's electron repulsion. And then I'm going to go to the next slide. The potassium and the sodium graphs are really wonky here. This is what they actually had you looking at. So what best explains the difference in binding energy for the 3s electrons? Did you guys have answer choices in yours? Okay. Basically, I need you to tell me A, B, C, and D. Don't actually tell me. Just looking across the board. Some of us just weren't there yet. Just give me a second to look. All right, I see a lot of hands going like this. Okay, so answer is A. Nuclear effective charge for potassium is what? Basically, potassium has how many protons? 19 protons, and sodium has 11 protons. So that makes a big difference when you're attracting your 3s subshell. So the distance of, so whose 3s subshell is closer to the nucleus? Say again? Potassium's, right? So it's closer to nucleus, which is giving it higher binding energy because of ZEF, because of nuclear effective charge. So the next question asks about intensity, right? Through 4B. So I don't have answer choices on here, but I think I didn't copy them. So what's the relative intensity of K versus potassiums versus sodiums? Whose is higher? Potassium. Why? Because it has higher what? Nope. Intensity. Guys, we got to remember, there's only two things you're looking at here. Like relative distance to the left or the right is binding energy. That has to do with what? Protons, ZEF, right? If you're going left and right on this graph, it's just because your protons are pulling the electrons closer to nucleus, higher binding energy. The intensity is different because why? Number of electrons. That is the only two things this graph really tells you. So why is potassium's intensity higher than that of sodium's? Has 2 electrons versus 1 electron. This is what? 4 or 3s? 1, 2, 3. So this is 3s2 because potassium has a full third energy level or a full third at 3s energy level. Sodium only has what? 3s1, so the intensity is different because of that. Okay. Can I move on? Yes, but this is specifically asking for 3s, so that 3s is a full subshell. Okay, so I'm going to point to the periodic table over there. If this is the 3s that it's speaking of, sodium only has 1 electron there, but potassium goes all the way through that. It goes to 4s1, so its 3s subshell is full. Okay. 5, but this is really just horrible graph. It's ugly. Okay, so take a second if you've not gotten there and consider answer choices. All right, come back to me here. Let's just talk about the answer choices one by one, and then we'll consider. Before we move on, I usually like to consider why these peaks are in different distances from the nucleus, just to verify distance from the nucleus, or sorry, binding energy is relevant to the what about the atom? The ZEF, right? So the number of protons. So oxygen has how many protons? 8 protons, okay. Ti, titanium, 22 protons. This is just us, just so we can have all of our data on the graph here together. Carbon has 6 protons, okay. So we see kind of a weird arrangement here. It is talking about like the 1s, the 2p, and the 1s. So they're talking about different sublevels. We have 8 protons, 22, and 6. Okay, we're going to have that in mind. Oxygen has more valence electrons than Ti. So we're looking at the relative positioning. Okay. Oxygen has more valence electrons than titanium or carbon, so it has more energy required to remove them. Can a PES diagram tell us that information? No, it has nothing to do with valence electrons. It has to do with how many electrons are in different subshells, and then zero electron repulsion plus the ZEP, but that's irrelevant here. B option is more electron repulsion in the 2p sublevel than Ti. Is that true or false? Say again? First of all, does oxygen's peak here represent the 2p? No, it's representing the 1s. So this data does not correlate with that answer choice, so we would not be able to choose that. Okay. Titanium atoms are present in greater quantity than oxygen and carbon in the mixture. You should be scratching your face up like, what? Like, that doesn't even make sense. This graph has nothing to do with quantity, right? This is not a mass spectrograph. Mass spectrographs gives us those intensity peaks based on like how the isotopes bombard the detector. This has nothing to do with quantity. This only has to do with what and what? Electron count and protons, really, right? So it was that. All right, titanium has a greater nuclear charge, but the 2p sublevel experiences greater shielding than the 1s sublevel. That sounds more relevant, right? Okay, so then we look up here. It is talking about the 2p, okay, so we're looking good so far. And so the titanium 2p is farther to the right, which should correlate with what this is explaining. So it experiences greater shielding. So what does that do to the binding energy? Right, it reduces it, so therefore it should be to the right. So that's the only answer choice that makes any sense with this graph. I don't necessarily like this question because it's really about seeing which of these is relevant to PES, but this was one that College Board gave us, so I'm using it. The answer choice should be D. Okay. All right, the last one is going to be drawing. Don't look on your paper for this one because I accidentally copied the answer, I think. So, no, I'm sorry, I have two more on this. I was thinking number 7. Okay, so question 6, given the spectrum of scandium below, which is the following, best explains why it commonly makes a 3+ as opposed to a 2+ charge. So take a second if you didn't get there. Just hold an answer up for me when you're ready. All right, come back to me. Let's get through each of these answer choices. Come back to me. Is that a P? There's no P answer choice at PHCJ. Okay, so removing 3 electrons releases more energy than removing 2 electrons. All right, so we're looking at, okay, let's label this out for ourselves, okay? So this first is 1s2, right? Keep going. Okay, so 1s2, 2s2, 2p6. Break in the graph just because there's a big difference, right? 3s2, 3p6, and so teeny tiny here, but I'm going to put 4s2 and this last one, 3d what? 1. Why is it bigger? I think they flipped these. Oh, I know it. Okay, so let's double check this. So we look at 4s2 and 3d1, right? But we look at the intensities of this, and that doesn't make sense the way this is written. And it's actually because the energy differences are swapped. So if you have a small peak and then a larger peak, what does a small peak have to represent in this case? 3d1, okay? Just FYI. that small first peak, it's probably really hard to see in your papers, but here we go. It's 3D1, and the second larger peak, 4s2. Okay, but still, we still have, what, 21 electrons? We have 21 electrons, we're good to go. All right, so removing 3 electrons releases more energy than removing 2 electrons. It's very, very, very close in energy. So removing 3 electrons will release a little bit more, but that is not necessarily why it's forming a 3+ charge. Okay, that might just be a true statement, but not why it's forming a 3+ charge. It's in group 3, and atoms only lose the number of electrons that will result in noble gas electron configuration. Is it in group 3? It depends on which group of 3 you're talking about. So I mean, it is in the group 3b, but not group 3a. And does it truly have 3 valence electrons? Truly has 2, but it has the ability to lose the last one. Okay, so maybe we'll come back to that because that's close, but not necessarily related to this PES diagram at all. The amount of energy required to remove an electron from the 3D sublevel is really close to that of the 4s sublevel, but significantly more energy is needed to remove the electrons from the 3p sublevel. Okay, so that is a true statement, right? And it relates to the graph, and it relates to energy from a PES diagram. So everything should be correlating. Don't just choose true facts. Choose things that relate to the data provided. So that should be the right answer, C. Okay. Removing 2 electrons alleviates the spin pairing repulsion in the 4s sublevel, so it's not as energetically favorable as emptying the 4s sublevel completely. No, because we're going to remove a 4s sublevel, but then we still have one lone 3D, so that wouldn't necessarily be true. So C is your best option there. And then 7, I think I copied the answer, so come back up here with me. If we have magnesium here, you can see the peaks. Go ahead and sketch this someplace for magnesium, and then overlay, so superimpose aluminum's spectrum on it. So just draw yourselves 2 small peaks, one that's triple the height, and then another small peak for magnesium, and then overlay aluminum on top. Give me a thumbs up when you're done with that. All right, so Taz, can you tell me what these, for magnesium, what these current peaks represent? Okay, 1s2, then 2p6, and 3s2. Okay, so relatively, where would you place the aluminum's 1s? Why to the left? Great, so magnesium has 12 protons, and aluminum has 13 protons. So it's got a higher Zeph, is what you're saying, so you're putting it to the left. How does the intensity differ? So what does intensity represent?
It represents the bonding energy.
No. What does intensity represent, guys? Number of electrons. Okay, so when I say intensity, what are you envisioning here? The peak size, right? The intensity of, like, the magnitude of the binding energy, I would not call that intensity. The magnitude of the binding energy is Zeph, is how close it is to the left or the right on this x-axis. The intensity is the peak size, which only represents one thing. Again, one more time. Electrons. All right, Taz, how would this intensity differ?
It would be the same.
Perfect, Taz, and always. You are perfect. 1s2 for aluminum is just to the left because it's got higher binding energy, but the intensity is the same. Marcus, how would the 2s peak differ?
On
But where would it be? Again, further to the left, so this is our 2s2. Chase, how would the 2p6 one differ, or how would the 2p one differ? How would the intensity differ? It would be the same. Thanks, Chase. Okay. And that's 2p6. All right, Drew, pick up on 3s. Say again? Same but to the left, and that's 3s2. And then what else do we have for aluminum, guys? All right, so how big is the 3p? Half of this size, okay, because it's the 2s represents 2 electrons, or sorry, the 3s represents 2 electrons. So the 3p one is going to be half size. Yay! Yeah.
Actually, I don't know if this is like a copying error on the advanced. Like the P for 2p6 is like to the left of 2s2. Is that like just wrong?
I don't know. I have to look back at that one. I just have my own answer. I'll look at it in a second. All right, so we're going to do two other things today. Open back up your package to the first page, I believe. That's where your textbook crumbs are. Is this it? It could be. It's not been necessarily copying error. So if we have to sketch our own, we don't know the binding energy exactly. We're just doing it relative. So that they have put this is the 2p6, right? They just put it to the left, but even more, because they probably had exact answers for the binding energy. Ours is just relative, so as long as it's in the correct place, you're good. All right, so you have 2 questions, 123 and 124. If you would, please start at 124, actually, for the moment. We didn't get to these yesterday, so start on number 124, which is in your packet. Is on the second page. Okay. It won't take you very long to achieve this, okay? Maybe like 2 or 3 minutes. Once you get done with that one, go back to the 123. Come back to me on this one. You should have had enough time to complete this question. Question A or 1, if it gives you NS2 NP4 as like the finalized electron configuration, please table, can you tell me how many valence electrons this element has?
6.
It has 6, right? So all you're doing is counting up the electron configuration. 1 or 2 plus 4 is 6. So that should have 6 VE, 6 valence electrons. because it's essentially telling you the tail end of the electron configuration, which is the valence shell. What are the possible identities for this element? JT's table.
Oxygen, sulfur.
Okay, so basically anybody in group what? Group 16 or group 6A, as we like to kind of isolate just the A elements, the representative elements. What's possible formula for this element? Megan's table? With potassium. Okay, so if you did sulfur, like potassium sulfide, K2S, because essentially if you know it's in, X, okay. If you know it's in group 6, what do you also know about it? The possible charge, which would be what? 2 minus when it gains 2 electrons to form octets, so that should be a possible ionic formula for that. Would this element have a larger or smaller radius than barium? Everybody? Smaller, because the radius runs this way, so in the end, anybody in group 6 has a higher what than barium? Higher Zeph. No. So higher Zeph. So Zeph is higher because you're farther to the right on the periodic table, meaning you have more protons. Group 6 would have more protons, meaning it's going to get smaller because of the higher Zeph. So these would be smaller than barium in all cases because the other ones are just super high, lesser energy levels. And then E, would it have a greater or smaller, i.e.? Smaller, because fluorine's one of the greatest, right? So it's definitely going to have a lower, and that's simply because of its lower Zeph with reference to fluorine. Okay, let's go to multiple choice now. Okay, so find the massive packet, massive choice area. I promise it's there. Excuse me? Yeah, that's it. So, do you see the parts where I've crossed out numbers? Like it says, you see from my handwriting, I'm in the next page. And this goes through 50 on the first page, and goes through what on the last page? 90. Oh my gosh, right? So, now, I'm going to give you a scantron because I am not calling out 90 letters, okay? But I want to see where we can get today. We have about 40 minutes left in class. So you'll see on homework I said I originally had 30 because I didn't think we get to this, but let's try to get through 40 today class. So I said for homework, finish through 50. So it gives you a little bit because you also have those like 3 FRQs you're working on. Okay? So we'll have about scantrons. You guys are working on multiple choice for a little bit. Normally I have you do these at home, but probably most of the time in class. Yeah, guys, separate from your colleagues if your colleagues are bothering you. If your colleagues are annoying and bothering you. Yeah, because I'm not. Oh, hold on, listen. Do not write on side 2. I will rip this scantron up if you write on side 2, because I'm not going to redouble your answers on side 1 and scan the same. Okay, so please write on side 1. Please write on side 1. I'm just going to scan this up. Side 1. Alright, last note on. There are a couple, I don't know exact numbers on the top of my head, but there are a couple that ask you to identify quantum numbers, like what are the possible quantum numbers up to P? We didn't go that much in depth in quantum, but you can do some quantum numbers. So the ones you can do for quantum, do. The ones you're like, nope, can't do this quantum question, skip. Okay? So there'll be a couple that are there early actually. I'm going to grade it on a scantron so that I'm not going to just score over the pen. I want you to go see your results. So be as accurate as you can so you can see what you need to study. Yeah.